Okay. So, we have just seen that dielectric loss in a cable, right. So, just we have discussed this regarding this one. This is the current and this is the voltage, and this is your this angle is called the loss angle, and this is your phase angle, that is the phase angle between current and voltage, right. So, in that case, so this we have already discussed. So, this one also we have discussed that dielectric loss in a cable is, just to memorize this, V I cos phi, and phi is equal to your 90 degree minus delta. So, phi is equal to 90 degree minus delta, this phi, because this is 90 degree. So, here your power loss will be V I sin delta, then V I cos 90 degree minus delta. So, power loss will be V I sin delta, but we know I is equal to omega c into V. So, put it here, I is equal to omega c into V, therefore, dielectric loss will be omega c V square sin delta, where C is the capacitance of the cable and V is the line to neutral voltage. Up to this we have seen. Next, what will come, that will come for the grading of the cables, right, because the value of Emax has to be kept within limits which depend on the margin of the safety and the permissible degree of dielectric heating. So, actually, since the insulation away from the core is under stress, that means, when you have a if we look at this diagram, if you just look at this diagram, suppose this is your core and this is your different your epsilon 1, epsilon 2, epsilon 3 different permittivity with different material for grading, but the question is that which is away from this core conductor, then insulation will be under stress, and insulation which is very close to the your core conductor, then it will be over stressed. So, that is why that insulation away from the core, that means insulation away from the core, which is away from the core, I suppose somewhere here say, right, is under stress. So, there is an avoidable waste of insulation. So, the avoidable waste of your, it is insulation, right. So, for this case you have to use methods which reduce the amount of insulation by redistribution of stress, so as to increase the stress in outer layers of insulation without increasing it at the conductor surface. That means, do not increase it here conductor at the your stress, you do not insulation stress here, that you do not increase it at the your near the conductor, but those insulation which are away from the core, it is under stress, but try to make it uniform, although not possible, but as much as possible you try to increase the stress, but without increasing your at the conductor your insulation and near the conductor surface or core conductor, right. So, therefore, by redistribution of stress, so as to increase the stress in outer layers of insulation without increasing at the conductor surface. So, two methods generally they use it. One is the two methods are recommended for this, capacitance grading, and second one is intersheath grading. These two things one has to see. So, although we will go for capacitance grading and intersheath grading, but in reality that implementation of these two are bit difficult one, but that is why rarely used, but we will see that how things can be done. For example, suppose this is actually, suppose you have a core, your core conductor, this is the conductor, right, core. So, two or more layers of dielectrics have a different permittivity. You have here in the diagram, this I have taken from a book, that in the diagram that there are three insulating materials are there having permittivity epsilon 1, epsilon 2 and epsilon 3. This is their electric field, your what you call that characteristic is plot, but 0 to r, then that is the conductor radius, then r to r1, r1 to r2, r2 capital R, but our interest is here only, right. So, with higher permittivity being nearer to the conductor, that means this epsilon 1 greater than epsilon 2 greater than epsilon 3, this is the ideas, because having different permittivities, those with higher permittivities being nearer to the conductor. that means epsilon 1 greater than equal to epsilon 2 greater than equal to epsilon 3. Now, the electric field intensity E x, say at any distance, here diagram it is not shown, say from the center of the your conductor, and you take at any distance x, that is electric field intensity E x, right, of radius, you take any distance x and its radius is your what you call x. Therefore, is given by your equation 5, that was already given. Just hold on, if I can bring equation 5 for you, right, just let me see where it is, just hold on, otherwise we will rewrite that is your, otherwise directly we will make it like this. Just hold on, let me have a look. Here it is not there, does not matter. If it were possible that electric field intensity E x, it is actually q by 2 pi epsilon 0 epsilon r x, that is the formula, equation 5, right. So, if it were permissible to verify to vary permittivity with radius x such that your epsilon r your inversely proportional to the 1 upon x, that means I mean if it happens so that if distance increases, this epsilon r will decreases. This one can be written as your m by x, m is a constant. So, in general your electric field that electric field intensity E x, that is equation 5, it is something like this, E x is equal to your q divided by 2 pi epsilon 0 epsilon r into x. This is the equation, right, that is actually equation 5. So, now if epsilon r is equal to m by x, then in that equation you substitute your epsilon r is equal to m by x. This is equation 5 actually. If you do so, it will be E x is equal to, it will be q upon 2 pi epsilon 0, then m by x into x. So, x will be cancelled. So, it will become actually q upon 2 pi 0 your 2 pi epsilon 0 into m. So, m is a constant, epsilon 0 is constant, pi is also constant and q is also constant. That means, this E x will be a constant value. This is equation 14, right. So, that means that E x actually, then that means if it follows this, if this property is followed, then E x will constant your everywhere E x will remain same, but in reality it is not, because epsilon r cannot be made inversely proportional to 1 upon x, but inversely proportional to the x. So, question is that your but based on that only we will proceed. So, therefore, from this formula only, so I told you that this remains constant. So, E x is constant throughout the thickness of the insulation. So, everywhere that wherever it is that electric field intensity E x remain constant, if assumption is epsilon r inversely proportional to the x, that is epsilon r is equal to m by x, right. Therefore, such a gradation is evidently not possible, right, it is not possible. However, 2 or 3 dielectrics with different values of relative permittivity can be used as shown in figure 6. But that is continuous thing is not possible, because epsilon r inversely proportional to the x, continuous that such thing is not available, but we can use 2 or 3 layers of dielectrics with different permittivity. This is epsilon 1, epsilon 2. Here in the figure there are 3 your insulating material with different permittivity, and I told you epsilon 1 greater than epsilon 2 greater than epsilon 3. So, with different that I showed in the figure 6, right. Now, from x is equal to r to x is equal to r 1, and I mean your this is conductor radius r, and from center to the first, that is your insulation sheet, first insulation, it is r 1, right. That means, at x is equal, that means from x is equal to r to x is equal to r 1, the dielectric with relative permittivity epsilon 1, because its relative permittivity is epsilon 1, right. So, that means at x is equal to r, E can be written as q upon 2 pi epsilon 0 epsilon 1 into r, because general formula is at distance x, it is q upon 2 pi epsilon 0 epsilon r into x, right. But x is equal to your r and x is equal to r 1, you have to see when x is equal to r, you can write that E is equal to q upon 2 pi epsilon 0 epsilon 1 into r, this is equation 15. Now, at x is equal to r 1, that is at x is equal to r 1, right, at a distance this one, this is for your insulating material whose permittivity epsilon 1. So, at x is equal to r 1, and first one we are considering, it is E is equal to q upon 2 pi epsilon 0 epsilon 1 into r 1, because it is here to here r 1, right. This is equation 16. Similarly, from x is equal to r 1 to x is equal to r 2, that is x is equal to r 1 to r 2, right. The second layer r 1 to r 2 permittivity is epsilon 2. That means, from x is equal to r 1 to x is equal to r 2, the dielectric with relative permittivity epsilon 2, because here permittivity is epsilon 2. That means, your just hold on. That means, at x is equal to r 1, right, E is equal to q by 2 pi epsilon 0 epsilon 2 r 1. Listen one thing, that this when x is equal to r 1, that is for permittivity or what you call insulating epsilon 1, it was q upon 2 pi epsilon 0 epsilon 1 r 1, but when it is this when it is going to the next insulating material epsilon 2 r 1 to r 2, but it is epsilon 2. That is why again at x is equal to r 1, E upon E is equal to q upon 2 pi epsilon 0 epsilon 2 to r 1, right. So, but not here epsilon 1, because for second year it is starting from r 1 to your r 2. So, it is epsilon 0 epsilon 2 your r 1, this is equation 17. Similarly, at x is equal to r 2, E is equal to q upon 2 pi epsilon 0 epsilon 2 into r 2, this is equation 18, right. So, from x is equal to r 2, now similarly from x is equal to r 2 to x is equal to r, that is the third one, that is x is equal to r 2 to r, right. The dielectric with relative permittivity here epsilon 3, the relative permittivity epsilon 3. Therefore, x at x is equal to r 2, it will be E is equal to q upon 2 pi epsilon 0 epsilon 3 r 2. Here this is for insulating 1, because this when it actually that r 2 is the beginning of the your what you call, that is the ending of this second this thing insulating material, and when it is go to epsilon 3, then r 2 is the beginning of this and capital R is the ending. That is why at x is equal to r 2, E is equal to q upon 2 pi epsilon 0 epsilon 3 r 2. Here also x is equal to r 2, the 2 pi, this is for your insulating material 2 epsilon 2, but again for insulating material 3, that is starting from r 2. So, E is equal to q upon 2 pi epsilon 0 epsilon 3 r 2. So, not 2, it is epsilon 3. So, this is equation 19. Similarly, at x is equal to r, that is the boundary one, last this one, surface one, right, that E is equal to q upon 2 pi epsilon 0 epsilon 3 r. So, this is your equation 20, right. I hope you have understood this. Now, therefore, just hold on. Therefore, using this equation, because if you look at all these equations, right, this E x is equal to is given, then you are at different values, that everywhere that we want to make that E is same, right. So, all these equations whatever it is there, you just equate to them, q 2 pi epsilon 0 all will be cancelled, just equate to them, please do yourself, just equate to them, all the E's are same, right. If it is so, I mean if it happens that all E at every point that E is same, then if they are equal, I mean we want equal electric field distribution, right, the trace, right. So, if all are equal, then your q upon 2 pi epsilon 0 will be cancelled, and finally, the equation will be 1 upon epsilon 1 r, right. That means, your this thing or what you call that 1 upon epsilon 1 r is equal to 1 upon epsilon 2 r 1 is equal to 1 upon epsilon 3 r 2, right. Just hold on. here, that it will be, if you equate with this one, q upon 2 pi epsilon 0 epsilon 1 r 1, right, and this is epsilon 1 r, all are equal actually. Therefore, we can write 1 upon epsilon 1 r equate to this with epsilon to this one, epsilon to with this equate this to 1 upon epsilon to r 1, then equate with this one 1 upon epsilon 3 r 2, right. So, that means q upon 2 pi epsilon 0 all will be cancelled, and finally, it is 1 upon epsilon 1 r equal to 1 upon epsilon 2 r 1 is equal to 1 upon epsilon 3 r 2. That means, epsilon 1 r is equal to epsilon 2 r 1 is equal to epsilon 3 r 2. This is equation 21, right. So, the variation of electric field intensity with radius is shown in figure 6. That means, this figure I showed you the electric field intensity variation, this one, this is the electric field intensity variation from r to r 1, r 1 to r 2, r 2 to capital R, right. Therefore, the operating voltage V is therefore, you integrate, no need to show the figure here, look r to r 1 E x dx plus r 1 to r 2 E x dx plus r 3 to capital R E x dx, right. Therefore, V is equal to r to r 1 q upon 2 pi epsilon 0 epsilon 1 x dx plus r 1 to r 2 you make q upon 2 pi epsilon 0 epsilon 2 x dx plus r 3 to r q upon 2 pi epsilon 0 epsilon 3 x dx. That means, this is for the first insulating material with permittivity epsilon 1, this is for the second insulating material with permittivity epsilon 2, and this is for the third insulating material with permittivity epsilon 3, right. Now, if you integrate, it is you will get q upon 2 pi epsilon 0 epsilon, it will be ln r 1 upon r, it will be q upon 2 pi epsilon 0 epsilon to ln r 2 by r 1, and this one will be plus q upon 2 pi epsilon 0 epsilon 3 ln capital R upon r 3, right. So, this is the expression of the your what you call the your voltage V, operating voltage V, this is the expression. Now, what you do, this all this equation, this is ln r 1 upon r. So, what you do, numerator and denominator multiply by r, here also it is r 2 by r 1, numerator and denominator you multiply by r 1, and here also numerator and denominator you multiply by r 3. If you do so, then it will be q upon 2 pi epsilon 0 epsilon 1 r ln r 1 upon r, the numerator and denominator multiplied by r. Similarly, here also multiplied by r 1 numerator and denominator. So, q upon 2 pi epsilon 0 epsilon to epsilon 1, it is r 1 ln r 2 upon r 1 plus here q upon 2 pi epsilon 0 epsilon r 2 into r 2 ln of r by r 2. That means, this is actually q upon 2 pi epsilon 0 epsilon 1 r, this is actually E max, because conductor radius is r. So, at the surface of the conductor that your electric field intensity will be maximum, that means, it will be E max actually, E max, this is at the surface of conductor, it will be q upon 2 pi epsilon 0 epsilon 1 r, right. Because earlier also I have told you that at the surface of the conductor that electric field intensity maximum. So, it will be q upon 2 pi epsilon 0 epsilon 1. So, this is E max actually, E max is equal to q upon 2 pi epsilon 0 epsilon r, then r ln r 1 by r plus r 1 ln r 2 upon r 1 plus r 2 ln capital R upon r 2. So, this is your voltage or what you call the operating voltage expression. When you use, in this case we have used three dielectrics, right, with different permittivities. Now, that is one thing. Second thing is that your intersheath grading, right. In this case, that what they do, that only one dielectric is used, only one dielectric will be used, but the dielectric is separated into 2 or more layers by thin metallic intersheath maintained at appropriate potential, right. I mean, here this is another diagram, this is the conductor, but you have that insulating material having same dielectrics, right, but you are then, but you are putting in between interseth. This is one interseth 1, another is interseth 2, and this interseth, if you can maintain that potential, I mean by some mechanism, right. So, maintain the appropriate potential by connecting them to tappings on the winding of the transformer feeding the cable. This is not easy procedure, right, but in any way. So, but if possible, connecting the tappings on the winding of the transformer feeding the cable. So, there is a fixed voltage between the inner and outer radii of each seat. So, there will be a fixed voltage then between inner and outer radius of the your what you call that interseeth. So, in this diagram 2 interseeths are shown, and this is actually some your characteristic is shown. This is your electric field intensity, it is given in kilovolt per millimeter. This is electric field with interseeth. When you put interseeth, the electric field, look this thing more or less they are following the same characteristic, but electric field without interseeth, this is showing the this one, that long curve, right. So, in this case there is a fixed voltage between the inner and outer radii of each seat, right. That means, so this is the figure, this is the figure 7, and this is actually this is the interseeth, outer seat, this is interseeth 2, interseeth 1, and here voltage is V, here it is V1, here it is V2. Now, so figure 7 shows this figure only, single core cable with 2 interseeths, the different radii are R, R1, R2 and capital R, right. The potential difference between conductor and first interseeth is V minus V1. So, this is at the surface, it is V, then V1, then V2. So, potential difference between the your what you call between the conductor and the first interseeth will be V minus V1. This is understandable. Thus, between the first and the second interseeth is actually V1 minus V2. Here it is V1, here it is V2. So, it will be V1 minus V2, and between the second interseeth and the outer seat, between the second and outer seat, it is actually V2. My question is, here it is only V2, right, because outer seat is V2. So, between your what you call that the first between the second interseeth and the outer seat. So, between the second interseeth and outer seat, it is taken V2. My question is why you have taken V2, right. Here we have not assumed outer seat, we have not assumed anything V1, V1 and V2. This is a question to you, that when you will read this, you mail me. This is the simplest answer actually, but leaving up to you, right. So, and if you answer this, I will reply to your mail when you read this, right. But here we have taken only V2, and this is the outer seat, right. So, using equation 9, the maximum voltage gradient in 3 sections are. So, first one between the conductor and the first seat, it is V minus V1. Therefore, Emax 1 will be, instead of V actually it will be V minus V1 R ln R1 or R. This is actually coming from equation 9. This is coming from equation 9, right. Therefore, that Emax 1 will be V minus V1 upon R ln R1 upon R. This is I am making equation 23A. Similarly, Emax 2 will be, that is between first and second interseeth, the voltage difference is V1 minus V2. Therefore, it will be V1 minus V2, that R1 ln R2 upon R1. This is equation 23B, right. And then this Emax 3 will be V2 upon R2 ln capital R upon R2. This is 23C. This is straightforward, you can write, right. So, in this case, if the values of maximum and minimum potential gradient in the 3 sections are kept the same, if you assume that they all are same, that is your what you call maximum and minimum potential gradient in the 3 sections are kept the same, then you will get R1 upon R is equal to R2 upon R1 is equal to capital R upon R2 is equal to alpha. So, in that case, if you try to make that they all are same, right, if you want to make this one all are same, that in that case what will happen, that R1 upon R is equal to R2 upon R1 is equal to capital R upon R2 is equal to alpha. That means, all this ratio it will be your what you call, they have to be same. In general, formula is V upon R ln your what you call ln capital R by small r, right. So, if you assume that all the things will be same, then this is the condition, that means if it is so, that means the your what you call the V minus V 1, if R 1 upon R is equal to R 2 upon R 1 is equal to capital R upon R 2 is equal to alpha, right, then this equation can be written as all are equal. So, V minus V 1 upon R small r into ln alpha, then is equal to V 1 minus V 2 upon R 1 ln alpha is equal to V 2 upon R 2 ln alpha. This is equation 25, right. If you want to make it this ratio, you have to make same, right. That means, if the cable does not have any interseat, suppose it does not have any interseat, in that case the maximum voltage gradient will be Emax will be V upon R small r ln capital R by small r, this is 26. If there is no interseat, then this is that Emax, because that is at the surface of the your conductor. So, using equation 23 and 26, the ratio of maximum trace with and without interseat can be calculated, because this is without any interseat, and other equation 23 means 23a, 23b and 23c, right, calculated. The radius of interseat can be found from equation 24. That means, from this equation that radius of the interseat you can find out from equation 24, right. So, when voltage V 1 and V 2 can be found from equation 25. I mean, there are 3 equations actually. This one is equal to this one equation, this one is equal to this one equation, and this one is equal to this one another equation, right. So, from that you can compute, if data are known you can solve this, if data are given, and you can find out V 1, V 2, V 3 etc., right. So, both the methods for grading of cables involve practical difficulties. There are practical difficulties of implementing this method. With capacitance grading, the difficulty exists in obtaining insulating materials having required values of permittivity. I mean, you have to put insulating materials of, suppose you are designing some cable, the different if you want that I want this much of electric field intensity strength, then different permittivity of insulating material, it is difficult to get, right. So, this is one disadvantage. So, it is almost not possible, although just hold on, although use of rubber, it has a permittivity value in between 4 to 6, and impregnated paper that permittivity value 3 to 4 have been suggested. I mean, you can, if you can use rubber, paper etc., is one thing, but rubber is very expensive and the cost of dielectric become prohibitive. Rubber is expensive. Moreover, possible changes of permittivity with time may alter the stress distribution and lead to insulation breakdown even at the working voltage. Then with the time there is a possibility the with the time this permittivity value may alter. In that case, there is a possibility of breakdown even at the working voltage also. Another thing, with interseat grading, it may be difficult to arrange the proper voltage of interseat, because you have to connect it to some transformer winding, tapping. So, these are very difficult tasks. So, that is very difficult to get the proper proper voltage, and the joining of cable having interseat also poses problem. Suppose you have cut the cable and 2 cable you are going for jointing, and if interseat is there, then it will be difficult because interseat will be spoiled. But the possibility of damage to the thin interseat during cable laying also exists, because when you are joining, right, damage to when you are laying the cable also, because interseat will be very thin, and there is a possibility that your what you call that this interseat may damage, right. So, these are the disadvantages of capacitance grading and your interseat, right. Thank you. We will come again.